I'm going to introduce one of our field engineers, Michael Harris. He's going to talk about making use of semantic search to conceptually search across languages terabytes. I will just give a little bit of a prompt here that what he's talking about is the nearest thing I've had in my career to pixie dust. The underlying capability with embeddings, you're going to hear several presenters talk about it, is next to miraculous. It underlies sentiment. We've used it to recognize events such as attacks in Army parlance. It is continuing to amaze us and is probably the most versatile tool in our toolbox. Michael?
Thanks for that introduction, Chris. I love that I'm up here about to talk about pixie dust. I could use my 8-year-old daughter right now. She would love this. All right. So my talk today is about scaling semantic search. And that's a lot of words that people probably have no idea what they mean. So let's start off with understanding what exactly am I talking about conceptually. The underlying technology of semantic search is what we call a text vector. And the best way to understand this is to think about latitude and longitude. Now, if I asked you, where is New York City? You could say, it's in New York. But another way to define the location is as what we geeks call a two-integer array. Basically, what I'm talking about is you have two numbers here, 127.15 for latitude, 113.45 for longitude. Two numbers to represent an idea. And if we know latitude and longitude for two different places, say for instance, New York City and Paris, we can calculate the distance computationally. There are several different formulas, mathematical formulas we can use to figure out that that distance is 5,570 miles. Or if you've ever flied coach, between those 2 points, another answer might be way too far. And so continuing on with this concept of latitude and longitude, what if we took numerical values and assigned them to words of an entire language? Words that are semantically similar, like vehicle, car, truck, plane, or in this example, pen, pencil, and writing, would be close to each other in value. But instead of 2 dimensions, like with latitude and longitude, we're going to need 300 dimensions to create a mapping between these words that can accurately provide us with distances. There are a lot more words in a language than there are places on the map. And words that are unrelated will be much farther away, numerically in value. And this is represented visually by the word wombat. You would never see, or most likely not see, wombat along with pen, pencil, and writing within our language. Furthermore, the models that store this information, they're created using deep learning and training data. One of these shortcomings of leveraging this deep learning method to create these models is that each time you run it, you'll get different numerical values for the words in a language. Therefore, when you train different languages, the words of each language, and I'm visually representing Spanish and English here, and again, if we think about latitude and longitude, coche in Spanish means car in English, and if this is our 2D representation of these two models, you can see they are not aligned. Koche is in the top left, cars in the bottom center. And this is a problem if we want to search for terms across different languages. And the way we resolve this is by analyzing each language model, and we align the same or similar words of each model to each other. Again, going back to latitude and longitude, if we look at our two language models here, casa and house are both in the top right, maybe not exactly positioned perfectly, but very close. Hombre and man, coche and car. So now that everyone here is now an NLP expert in text vectors, let's talk about what can we do with this technology. As Chris says, what does this pixie dust get us? There's several things that it can do. Number one is eliminate close matches. The current state of the art for eliminating close matches, if you have huge volumes of data, you're probably going to have some data that is a duplicate of another. Well, if it's an identical duplicate, it's really easy to use what we would call a hashtag or a hashing function to find those duplicates and get rid of them. But it gets much harder if you have two files that are the same but slightly different. An example of this might be you have a text document and an audio document that were covering the exact same corpus. You're probably going to have either misspellings or slight differences in between those documents. And eliminating those duplicates, finding those duplicates using text vector technology is a great use there, and it's very good at that. In the same vein, if you're searching for similar documents, say you're looking for a Venezuelan militia that's plotting a coup, and you have a document, and you'd like to find other data similar to it, and you have millions and millions of documents, and not a lot of time, right? You may not want to read through a huge document about this Venezuelan coup and find the actors involved, the code names, the specific keywords related to it, figure that all out, put it into a search, and look for it. Well, what you could use with this technology is you can actually get the vector value of that document, the whole document, all the words together, and then search your repository for other documents that are a close match. And miraculously, this actually does work quite well. Another example is searching for close proximity topics or themes. More specifically, you can use this for targeted event detection. It's very difficult for computers to detect what we as humans classify as an event. Current technology typically takes a rules-based approach to figure this out. And the problem with that is that if you're specifying rules for a certain event, this is very brittle. And it requires constant upkeep and maintenance. If you use text vectors and semantic searching, it's quite flexible for matching hits. And an example is over the summer, we worked on a project for the Department of Defense where we were provided with cable data, and we were asked to target 3 specific events: phone communications, battles or attacks, and cash transactions. And using text vectors and semantic searching, we're able to locate those events with a high degree of accuracy without necessarily having rules or specific keyword matches. You can also set up alerts based on similarity, which can be pretty interesting. If I need an alert for anything related to, let's say, Russian nuclear-powered space vehicles, but I don't know the name of the vehicles, I don't know anybody involved in the program, and I really have very little knowledge of anything other than I'm looking for these types of devices. You can search your repository of documents using those terms, and you'll get things back that match. Which brings me to my last example. it's really good for multilingual search. And here in the US, most of us speak English, and so you can actually have search based on English input against a repository of documents that are non-English. To go back to our Russian nuclear-powered space vehicle example, if all of my documents are Russian and Arabic, I don't need to worry about translating nuclear-powered space vehicle and have the problems that go along with that. Chris mentioned, Al Raqqa, when you translate that, you don't actually get the city. And so those are problems with translation. Also, I don't know Arabic. I can't read Cyrillic. I'm not going to know if the translation was off, if I have a misspelling. I would much prefer to search in English. And multilingual search, when we align those different models, this is a capability that you can use this technology for. So hopefully I've sold you on what you can do with this technology. It's pretty interesting. It's really cutting edge as far as what can be done. But the problem with it is that when we're comparing those two documents, the vectors of those documents, the comparison is slow. And I doubt anyone in here goes into a meeting and talks about their small data. Does anybody go out and read the news and hear, articles about tiny data? No, it's all huge data. It's all big data. And to give you an example, a terabyte of text broken out by paragraph is 1.8 billion rows of data. The standard approach to calculating the distance between vectors is done using something called cosine distance or Euclidean distance. And once you go above a couple 100,000 comparisons, it's not really feasible to use this technology in any real-world way. Unless, of course, you have a supercomputer or a quantum computer, it's not going to work. And just to give you an example, if you had the world's second fastest supercomputer at the Lawrence Livermore National Laboratory, it has 1.5 million processor cores. That's what you would need to process our 1.8 billion rows of data in about a second. That's a lot of computing power. And so over the summer, I was tasked with figuring out, how do we take this technology and actually use it? And what I tried first was running Python. And I was able to get to 3,700 comparisons a second. And that's not too fast, especially when thinking in terms of billions of rows of data or comparisons that we want to make. So I spanked the turtle. I hit it as hard as I could. I felt like the jockey there who's not going too fast. And I was able to get up to about 6,900 comparisons per second when I updated my code to be multi-threaded. Again, not quite what we need. And as an example, that 1.8 billion rows of data running on an Amazon instance, an R5 2x large, which if you're not familiar with what that is, it is neither the slowest computer that's out there, but neither the fastest. It's roughly something in between. And that's where I got these numbers. But that would take 74 hours to perform a single query against 1.8 billion rows of data. Who here has 74 hours to run a query? Right. So we have a need for speed. And the answer to this problem is something called indexing. Using an open source library called Annoy, I was able to achieve 48 million comparisons a second. My lawyers told me I have to use the word near perfect accuracy, but it was pretty much dead on. That's much better than 6,700 comparisons per second. Furthermore, though, if we want to get into the billions, we have to push that a little bit farther. If you can accept a little bit less accuracy, you can get throughput of above 400 million records per second. And to drive this home and let you know what I'm talking about, in my testing, I had 2.4 million rows of data, and my search returned 15 of 25 hits as compared to Python, the record of truth. So basically what that means is that out of 25 records I brought back, 15 were as close as you're going to get when looking at the record of truth. The next 10 were slightly farther apart than the record of truth. And when you get to that number, now our terabyte of data can be searched in a few seconds, and we don't need quantum mechanics or a supercomputer to do it. There are some challenges to using an index, though. It's not a silver bullet. It doesn't solve the problem completely, in that it's fast and it's sleek, kind of like Batman's motorcycle. But guess what? You still have to load it. You still have to fill it up. A 2.4 million row index, which was the data that I was working with, had a load time of about 12 minutes. And again, to take that out and extrapolate to our 1.8 billion row example, that is about 12.5 hours with 12 servers. And again, you could horizontally scale that. You could get that number down to 6 hours with 25 servers, and so forth and so on. But that is a challenge of using an indexing method to solve this problem. The other problem is that you can't iteratively add data to an existing index. It would be great if we could load that data once, even if it took days or a week, and then as new data came in, just append that data to our index, but you can't. It's simply not the way the technology works. So one possible solution is to create another index when you have another data collection that comes in. But that's not a perfect solution either. And as an example, if you were to query two indexes looking for the 20 closest terms, if you took the first 10 results from one, the first 10 results from the other, it's quite possible that results 11 through 20 in that first index that you didn't see could have been a closer hit than 1 through 10, the 1 through 10 results of your second index. So one of the other things I want to talk about is, indexing is great, it's cool, it's solved the performance problem to some degree, but it's no good if it takes a team of PhDs and a room full of engineers to actually use this in the real world and make it work. And what you're looking at here is about 10 lines of Python code to create an index. And I'll just step through it very quickly. T equals Illinois index 300. 300 is the array size. Remember when I said latitude and longitude is a two-dimensional array? And when we leverage text vector technology, we have no less than 300 dimensions. That's what that is telling it there. T.add item, that's adding an item to our index. It takes an integer and the vector value. That integer can be mapped back to your data repository, whether you're using a CSV file or a database or another data store. T.build 10. 10 is the size of is the number of trees in your index. And to simplify this down to make it understandable, basically the more trees you have, the longer it takes to build your index and the larger it will be, but the faster and more accurate your queries will be. And then T.save, one of the more unique things about Annoy is that it actually saves your index as a flat file. And this is really interesting because you can take that flat file and you can back it up, you can save it, you don't have to worry about losing your data, and you can also share it among your organization. So if you wanted to have a search based off of a certain collection, you can take that index, you can share it as a file to any organization or other group that might need it, and they can use that for their searches or other means. Next up, this is showing you how to run a query. Again, super, super simple. This is Python code. We're looking at roughly 4 lines of code. We pass in a vector value that is v. That's going to be your numerical value representing a word or a document or a group of words. Let it know the number of results that we want to get back. Distances equals true is exactly what you think it is. This will return the distance between your search terms, and is a powerful thing because you can set thresholds and cutoffs depending on your data, depending on your needs. You can say, I don't need to see anything that's farther away than this. Search k equals 20. That's the other tool that you can use to balance load time versus query time. The higher that number, the more accurate your results will be. However, the slower your search will come back. And what I would like to do next is actually demo this for you. I have that 2.4 million row index running in the cloud. Before I do it, I just want to explain the results that you're going to see back. This is an example of the schema. We have an ID, which is just a number, the doc type, which it's either going to be a document or a sentence. If it's a document, we're going to get the file path back, which is actually the title of the document. If it's a sentence, we'll actually get the sentence back. And of course, we stored the vector value of all those documents and sentences in the database.
So I'll try and make that a little bit bigger if I can so people can read that text. So just to give everybody a quick refresh, this is actually running in the cloud. I've got a database with a lot of vectors in it, and we'll run some terms against it, see how fast it is and what we get back. So the first search that I'll run is in Spanish. It's hijos de inmigrantes, and if you're a fluent Spanish speaker, I apologize if I butcher anything there. But to translate that to English, these are children of immigrants, is what we're searching for. And I brought back 10 results here. These are the 10 closest matches from the documents that I have in my database. Again, as a reminder, I have both documents and sentences. If it's a document, you're going to see the word document in front of it. Our number one hit, the closest match to those terms, was an English document, the title of which is Immigrant Children, Here's What's Happening with Kids at the Border. We have a couple other English documents there, the current administration's immigration policy, and for those of you who can read Spanish, there were several sentence hits that we got talking about children of immigrants. I'll run another example, and this is both an example of targeting, which I talked about earlier, or specific event targeting, and it's also an example of fuzzy searching. What we're going to search for is computer attacks. And what we get back, the closest hit was a document. FBI warns consumers to reboot routers that may have been hacked. We also have other sentences here related to cyber warfare, cyber criminals, cyber attacks. You'll notice that In some cases, we do get direct hits for the two words that we use, but in many cases, we don't. And that's really the power and the flexibility of using this technology. One other thing that I'll point out that you may not have noticed is I actually have the runtime here for each of these searches. That's in seconds. So that's 0.003 seconds, which is incredibly fast. Considering the amount of data that we just compared to those search terms. That was the demo that I had prepared. If anyone has any questions, we'll take a minute or two to answer questions. Yes?
Good morning. I noticed that the documents that I can see anyway are all .text. Is this a tool to find documents such as .pdf or other document formats besides?
Sure. So, sure, I'll repeat the question. He was asking, the documents that came back are all .txt files, and he was asking, can the system work with other formats? The system will work with textual data. If you have PDFs or other things of that nature, there are tools you can use to extract the text from a PDF. Same thing with images. There are tools out there to pull the text that might be represented by an image. But essentially, all you need to do is pass that text to get a vector value. But to answer your question, yes, we work with lots of different file formats, but those file formats, you'd have to use some sort of tool to get the text out of it. It works with text data. Yes?
No, I was just thinking for the benefit of the audience that I think you mentioned it in your talk, but maybe you want to review just quickly the size of your corpus, what the kind of languages in the corpus, like what the search looks great and fast, but I could search 10 docs on my laptop. So I know you're doing more, and maybe you want to expound a little bit.
Sure. So the repository we're searching against, I scraped the internet and grabbed stuff from different news sites. I think there were 3 or 4 languages represented. Spanish was one of them. The large body of corpus, probably 80% was English. And there were roughly 2.4 million rows of data. So we're running that many vector comparisons every time we do a search. So that gives you an idea as to just how fast this thing is. Yes?
What's the vector size that you guys are using for this? Or
I'm sorry, can you say that again?
The size of the vector, as in you said, there's like 2 or 5 or
Yes.
300?
So the vector is 300 dimensions. So there are roughly 300 integer values representing a document or a sentence or a word. Yes?
Yes, Michael, what are some ways that you try to approach evaluating the quality of the results that you get back? Because it's a little less straightforward than evaluating the results of a Boolean-based query, for example. So like your result 5 and 6, on the surface, they don't seem related to your query. But I just wonder if you could talk through some ways you've thought about evaluating the quality of the search.
Absolutely. So as far as what you're seeing here and how they're ranked, they're being ranked by distance. And as far as comparing, if you remember my talk from earlier, there's search K, and there's also the number of trees that you can provide when you're loading your index, and that affects accuracy. And so these searches are a balance of accuracy versus speed. And one of the things I mentioned was that in my testing, I was finding that roughly 15 of the results, earlier when I tried this, I was pulling back 25 results. I got 15 of 25 were a perfect hit as compared to Python. Python, running that cosine or Euclidean distance, is your record of accuracy and perfect hits. And so I could compare these results to what I got in Python and know just sort of what my accuracy was. Does that answer your question?
Yeah, so I guess you're saying you use the distance as what you're optimizing for, and when it comes to accuracy.
Yes.
But you're not using, there's not, at least in this implementation, you're not considering other factors like whether or not that item is actually about what the user thought they were searching for.
Sure, and I think to actually look at, well, I can't look at 2.4 million documents and rank them, and even if I did, I think it would be very subjective. But to your point, with text vector technology, you're not necessarily always going to get the way a human would subjectively rank these. But you will, when sorting through millions of rows of documents, you'll find that it is helpful and that you're going to get a lot of close hits back. Will everything be perfect? No. Yes?
Back again. Are you capable of searching in character sets besides the Greco-Roman, for instance, characters, or some Sino-Indian characters?
Please repeat the question.
Yeah, so he was asking if I could perform a search using other character sets, such as Cyrillic or non-Roman characters. I believe so.
Yes.
Yeah, yes.
Everything we're going to show today works across the entirety of Unicode. And this is where you can get especially surprising results given the appropriate corpus on which you train. Back to what I spoke about, you can even get matches from, say, words like this to emoji.
So I don't want to take up too much time. We'll take
We'll have
one more
more
question.
here.
Yep.
So two questions. One is, what is the embedding that you're using? Is it word2vec? Is it GLOW? What is the underlying embedding technology? And second is, how do you go from English space to Spanish space? Is it a translation? Is it dictionary lookup? What is underlying technology?
Sure.
Let me defer that one to our next speaker who did the engineering behind this and can go into that level of depth. So actually hold that and we'll give it to Kafir.
All right. Thank you.